Good afternoon, everybody. I'm Amarjyoti. I'm working in National Center for Medium Range Weather Forecasting, and I'm going to present my work on variability of raindrop size distribution and its impact on polarimetric rain rate estimators. Before I start my presentation, as we all know and in earlier presentations we have seen that one of the most difficult parameter to quantify and even till today is the rain rate estimation. And this is my baseline for my work. Yeah, so this is the outline of my work. I'm going to talk on polarimetric radars, just one line, and then the parameters that come from polarimetric radars and the data and the scattering simulations what I've done for the estimation of my polarimetric parameters. And then second part comes the rain rate estimators, and I'm going to talk about the DST seasonal variations. Of course, today morning I have learned that the terminology that southwest and northeast monsoon, which can be corrected in future. And then the three polarimetric estimators. First one is RZH. This is only single polarized rain rate estimator, and the second is rain rate using two parameters, and third is KDP, and finally I'm going to conclude it. Yeah. I don't know how many of you all have attended this Ernie's presentation where he told the advantages of polarimetric radar when compared to single polarized radar. The single polarized radar, where we have only few parameters like reflectivity, velocity and spectral width, where reflectivity being the only parameter for the estimation of rain rate. The rain rate estimation using reflectivity, because it is also having its dependency on drop size distribution. And in the year 1979, Batten has given his variability of ZR relation with various coefficients. We all work on seeing how much is the rain rate this year, that year, and prior to that there is so much of work done on what should be the coefficient that we should use for the estimation of rain rate. And today I am going to present how these coefficients will vary and have its impact on its drop size distribution. And the polarimetric parameters, polarimetric radar typically transmits in two polarization, horizontal and vertical, and they have become more popular when compared to single polarized radars in the recent centuries because of, recent decades, is because of its higher ability to find improved quantitative precipitation estimation, identifying hails separating from rain, and then identification of various hydrometeors. And not only hydrometeors, the non-meteorological echoes like birds, insects, etc. And these are the pictures. We are coming to the polarimetric radar parameters. The single polarized radar have only three parameters, as I said, reflectivity, velocity and spectral width. And in addition, we have parameters differential reflectivity, correlation coefficient, differential propagation phase, and the derived parameter, namely specific differential phase. As each parameter has got its own advantages and disadvantages. And for the simulation work of especially the DST variations, I have taken Gadanki as a location, that is in near Tirupati in Andhra Pradesh, and I've taken 4 years of disdrometer data. Yeah. The scattering simulations, for doing this scattering simulation, see, actually I've done this work especially for the X-band polarimetric radar, which is going to coming up at Gadanki, that is National Atmospheric Research Laboratory. It requires, as I said, various parameters, especially for rain rate. When we find this much is a rain rate, so there are certain coefficients that are involved. So for this background work I have done also on the how to retrieve the DST parameters, and also the attenuation, which is a very prior and important role it plays in when it comes to the X-band radar. And for the simulation, the X-band frequency, this is the coming up X-band radar frequency, that's 9.368 gigahertz, and the temperature is 20 degrees, and the drop size distribution model, what I've considered is the Perpetual Beard model. And this is already, I've told 4 years of, yeah. As I said, Batten has told that the rain rate which we derive from reflectivity, and reflectivity is higher dependency on the drop size distribution. To be more specific, I'll just tell, suppose we have two volumes, and the first volume is having only 4 bigger drops, and the second box where we are having some 10 smaller drops. When we see with respect to radar, both contribute the same amount of reflectivity, and definitely when you get the same amount of reflectivity, the rain rate which is contributed by both boxes will be the same. It is same thing. If you have two volumes, then the both volumes will give same reflectivity, but it is not the case in case of polarimetric radar, because it has its specific parameter called differential reflectivity, which is totally dependent on the drop size. So by using all these additional parameters, I can retrieve my drop size distribution parameters. Now coming to the DSD variations, I've taken various rain rate intervals, and as said, southwest monsoon and northeast monsoon, I've taken 2 to 4, 8 to 12, 25 to 30 and 50 to 55. The reason for taking these intervals is like we have seen a significant amount of change in the drop size distribution southwest monsoon and northeast monsoon. So I just studied whether these variations will have its impact on my rain rate estimators. Yeah, so these are my simulated parameters. I'm not going in depth of how each simulation steps I've carried out, but these are the first figure, that is the color. Yeah, this is the one which shows the drop size distribution, and the red mark. Yeah, the red points to the convective zone, and the blue marks the stratiform zone. So the reason for separating this convective and stratiform, even though I said it is seasonal variation, even in each season we are having this thunderstorm showers and other rain events or storms, etc. But convective has got its own importance. Like, as we can see that in case of convective storm, the drop size is in the leading edge, it's around 4 mm. But when we see in case of stratiform, it is crossing 3. I mean to say, if you see the peak level, it is not even crossing the 2 mm. And the trailing edge is in between 2 to 3 in case of a convective event. And this is, maybe this plays a very significant role when we see the rain rate coefficients. And what we find is like differential reflectivity and horizontal reflectivity for the corresponding events, and this event is a continuous time scale of more than 4.5 hours. This is a temporal variation plot, and this is another case in case of 29th October 2009. This also shows that in case of this is of course a sample event what I have considered. Even in here we can see the convective, the trailing edge, but what we see is like, of course, this season it is expected that we don't have much of our very long-term events, or if we have also not that high as what we see in southwest monsoon or in pre-monsoon season also. These are the basically 3 different rain rate estimators, that is ZR relation. Z equal to, this is a very popular relation, Z equal to A1 R to the power of P1, and as we all know, the variability of reflectivity and its dependency of drop size distribution. And the second is a multi-parameter model. The differential reflectivity will give much better information of the drop size. So this is a multi-parameter model which reduces the whatever influence of the variability that is present in ZH. And the third is the KDP. As is a phase parameter, it is immune to partial beam blockages, and it has got many advantages. So this is a third relation. In addition, there are so many relations, but I have constrained it to only 3. And this is table 1, which shows the coefficients of ZR relation for convective, stratiform, and all. I mean to say that I have given a combined relation, because when we do at the instant when the radar is scanning, it is, yeah, we can separate the convective rain and the stratiform rain, but generally what we do is that we use a combined relation for all the 100 kilometer spatial and the continuous range, or we don't divide into regions, and this region, this is a relation, so we don't do that. So that is the reason for me that I am showing the combined relation. This is a pre-monsoon, southwest monsoon and northeast monsoon. What we see is like convective and stratiform rain, there is significant difference in the coefficient A1. Not of course in the coefficient, not that significant what we find in the coefficient B1. And there is large, even after separating in the season also convective and stratiform, still the scatter persists in the ZR relation, that is very clearly seen. All this scatters. And this is a stratiform, and this is a convective collection of data. And this is a type 2 where it is a multi-parameter model, and here also we find if we use a multi-parameter model whether any difference what we find in the coefficients. Here what we see is like, yes, even after separating or using a multi-parameter model, we have differences in the coefficients. And the third is the coefficient, that is rain rate using the specific differential phase. Here what we see is like, here the scatter is not as what we find in the ZR relation. The reason is KDP, if we see Z, it is actually related to the d to the power of 6 and into the distribution whatever is the n of d. But when it comes to KDP, it is actually d to the power of 3.44, approximately 4, that is approximately equal to the what we get for rain rate also. So it's a dependency on the drop size distribution has reduced. So that is what we see, a less scatter here when compared to what we see in the ZR relation. And this is a sample 27th night to 20th July 2007, where I've compared the true rain rate what I get from disdrometer with all the 3 rain rate relations. And what I see is like ZR relation in stratiform, it is overestimating when compared to what we have in the, here we see it's overestimating when compared to the disdrometer derived rain. And in case of convective, we see that there is some portion where it is underestimated. This is only sample case of one rain event where we find, if you see the statistical error matrices, it is clear that even at least for one rain rate, there is a significant amount of 10 mm difference in rainfall amount when we do with respect to ZR relation. So just you can imagine that for one event which I have collected for only 5 hours, there is a significant amount of 10 mm, and it is having because of the coefficient what I am using. So I think this will tell like why I have done this seasonal coefficients deriving and also the convective and stratiform in order to get a accurate rain rate estimation. That's what I started my presentation is like quantification of accurate rain rate estimation is important. And this I want to conclude my present talk by the impact of variability of DST on polarimetric rainfall estimators have been studied. 3 different rain rate estimators from polarimetric variables, that is RZH, and KDP have been derived for both stratiform and convective seasons. And this is RKDP. The scatter is less as I have already discussed, and in spite of segregating all that, the scatter still persists. Yeah, these are the references that I have used for this. Thank you.
Okay, maybe we'll move to the next person.
Thank you.
Good afternoon, everybody. Myself, researcher, and I am working in Kund Institute of Marine Environment Development, Himachal Pradesh. So I am working on aerosol and glacier studies over the northwestern Himalaya. So in this study, I took aerosols status to find out the status in over the Beas glaciers. So background of our study is the rapid urbanizations and industrialization in Himalaya over a few decades have led to a substantial increase in the atmosphere, evidences of aerosols, which can significantly affect climate and environment in Himalayan region. And the objective of study is to study the AOD with respect to spectral variation using sun photometers, and to study black carbon concentration using atherometers, to estimate incoming solar flux reaching at a snow surface by using pyrometers, to obtain aerosol relative forcing. So for this study, you can see geographical location of Beas glaciers, which is in the north side of Zemu Valley. And this glacier is important because this glacier fed to river Beas, and river Beas is the source of irrigation to Himachal Pradesh and Punjab regions. So that's why we find out the aerosol status and its impact on these glaciers. So methodology and equipments for aerosol studies, we use equipments like fine particulate sampler for PM 2.5 and sun photometer for aerosol optical thickness and chromatograph for ionic components and trace metals and portable atherometer for PC concentration and pyranometer for solar flux. But at present, in my presentation, I am able to show only sun photometer data and ionic data with help of ionic chromatography. Because we don't have at present this equipment. Sorry. So at present we don't have this equipment. It is in process. So that's why I am showing only data of this equipment, sun photometers. So result of AOD at Beas Glacier, so mean concentration at 500 nanometer is 0.2 and maximum is 0.16 on 1st October and minimum found at 0.1 in 3rd October. So on 1st October, why aerosol optical depth is high? Because there can be a possibility of external sources which can derive from the back trajectory analysis and MODIS images level 3. 1st October you can see there is a green color because of high AOD. With the help of back trajectory we can analyze the air comes in steady area from 4,000 meter, and internal or local source can be a rock bathering, because you can see in this image there is a rock bathering process and which scatter on the maximum aerosols. And ionic composition in Glacier Valley, I took some of samples from accumulation zone, crevasses and snouts. So dominant ion component is sulfate, which is 17.2 milligram per liter on snout, and followed by nitrite, and which is on surf. And dominant cations are calcium and on snout, and followed by ammonium, which is 1.4 microgram per liter on surf. And chloride found minimum at all sampling sites in Beas glaciers. So conclusion of the study, transportation of dissolved dust fine particles due to high AOD or AOD at Beas glacier, which is called snow surface tracking in ions, nitrite and sulfate observe maximum, while in cations, calcium and ammonium observe maximum at the snow surface. Possible source can be fertilizer, fossil fuels and biomass burning in this region. And expected outcome and future targets of our objective is to that in-depth study of aerosol or glacier methodology for policies, plans and programs in Himalayan regions, and understanding aerosol mediated changes in snow and meteorology, forcing and surface temperature over snow surface, and especially in the Himalayan regions. Thank you.
Thank you, sir. Thank you. Next, Krishna Kumar. No? Okay, Kishore Kumar, I think we have Kumar Pratibha. Yeah. Also Kumar, okay. Yes.
Hello, good afternoon all of you. Myself Lokesh Patel from NCR Goa. Just now we have initiated our study in this Western Himalayan region. We have chosen this reason because the Himalaya is not melting. And these are the main source of water for the 50 to 60% of the rivers. And the Glacier is situated in the Western Himalaya. This is in the Venus Basin. which has higher number of glacier as compared to Ganga and Brahmaputra. Yeah, this is the 3D view of the Western IISc study site. You can see the topography. Sorry. This is the glacier. It has the lowest height 4,400 meters and highest altitude 6,200. This is the Chandra region near the Sikkim glacier, and this was the Chota Sikkim glacier. Yeah. This one has a maximum level of 4,020 meter and highest elevation of 6,200 meter. The total coverage of the glacier area it has 25.25 square kilometer, and it's a main valley. This one. From there to here, this is the main valley. It has 11.2 kilometer height. Oh, sorry, 11.2 kilometers length. And its orientation, its accumulation area is oriented to northward, and its ablation area is oriented towards northeastern side. It has slopes is vary from 0 to 40 degree. And it has a debris cover 0 to 7 centimeter. Actually, to measure the debris thickness, we have included only the thick debris. So sorry, small particle of debris, which has 0 to centimeter, very small 0 to centimeter, 7 centimeters. Now, as per the India water portal, we have monitored the last 100 years data set of temperature and climate, and we found that trend. The most of the precipitation is in this July. So actually, I have divided our study into 3 parts. First, we have monitored the glacier fluctuation using satellite data, and second, we have monitored the mass balance study using glacier retreat using mass balance techniques, and third, we have monitored the hydrological analysis. We have analyzed the hydrological balance of the glacier area. So here for the analysis, for analyzing the glacier fluctuation, we use the Landsat 8 data of 2013, and for 2000 we use Landsat ETM plus, and for 1989 we use Landsat TM. And we have processed all the data sets. We have processed all the data sets with the reference of SOI topography. And also we use the ground data for the validation. And I have extracted manually the glacier boundary and just compare what is the last 25 years fluctuation in area, terminal and VLA. Here. Then I found out that in the first decade, since 1989 to 2000, it was lower as compared to this current decade. And the rate of terminal fluctuation was 9.93 meters per year, and its equilibrium line was shifted from 5,200 to 5286, like that. And second part, mass balance study. Yes, 1 minute. Mass balance is the measurement of the total gain and loss of the glacier mass, and it's divided by its density. Here, to measure the mass balance, we have used this stream grid, and we have installed a vertical total we have installed 21 stacks along the valley from 4,800 to 5,300 meters, and 17 stacks to ablation zone and 4 stacks in the accumulation zone. And after 15 days, we have monitored the retreat of the glacier, and we found this. We found that as we are moving upward side, we found that it has a higher retreat as compared to the lower portion. And third part, hydrological analysis. To measure the stream flow and stream discharge of that area, we have measured the first velocity of in the center part, right part, and left bank of the river. And after that, we multiplied it with the area of the cross-sectional area. Then we find out when we got the result, its discharge varied from morning to evening, and highest discharge was 12 meter cube per second. Thank you.
There are a lot of glacier talks. Any question on that? Those who are working on glaciers. So next is Madhu Singh.
of you. I'm going to talk about impact of Mediterranean oscillation on onset of Indian summer monsoon. Onset of Indian summer monsoon shows large interannual variability, and we know there are three different epochs of monsoon: onset phase, active break, and withdrawal phase. Onset phase shows highest variability in rainfall amount, that is 60 to 70%, and active break shows 50 to 60%. Withdrawal phase shows 30 to 40%. That is not part of my study. So, other studies have identified northward propagating interseasonal variability as one of the most influencing factors responsible for early and delayed onset of Indian summer monsoon. The northward propagating interseasonal variability carry a large amount of moisture and momentum from tropics to subtropics, which deliver a strong pulse of perturbation over Indian subcontinent. So, MGO can be regarded as the holy grail of the tropical atmospheric dynamics. It's a ocean-atmospheric interaction. Interseasonal perturbations coherent with MGO exist in the equatorial Indian Ocean during progress of monsoon. So, my focus of this study is on the progress of monsoon. Fast response of northward propagating interseasonal variabilities to onset of ISM occur during interseasonal variability that we define as ISVO years, and non-ISVO years are those years in which there is no significant contribution of this interseasonal variability to the onset of Indian summer monsoon. Now, I'm using IMT product for onset date, and for this study I have used onset date over Kerala and onset date over West Rajasthan. So what I have done, I have calculated the progress of monsoon. Means when monsoon sets over Southeast Arabian Sea, and how it means number of days it takes to progress over western part of the country. So I am using GPCP precipitation data, that is 2.5 degree cross 2.5 degree, and NOAA wind data 2.5 degree cross 2.5 degree, NOAA interpolated OLR data 2.5 degree cross 2.5 degree, and for calculating MGO state, by MGO state I mean phase of MGO and strength of MGO. I have used Wheeler-Heron indices, that is real-time multivariate indices RM1 and RM2. So these are the wind plot, precipitation and wind climatology for the data period 1979 to 2013. So you can from this I have taken for month of May, month of June. This is wind and precipitation climatology for the month of May, just prior to the onset of summer monsoon and after the onset of summer monsoon. So you can see positive rainfall anomaly over Southeast Arabian Sea and over Bay of Bengal during month of May, and it progressed over Indian subcontinent during month of June, and these are the fluctuations which we can see in month of July. these are the composite OLR anomaly curves. So you can see negative polar anomaly over Southeast Arabian Sea and over Bay of Bengal. So positive polar anomalies enhanced convective regions, and you can see negative polar anomaly over this region. So it shows region of suppressed convection. So for month of May, it is for month of May, and you can see during June this positive polar anomaly over Arabian Sea. This OTC is date, oceanic tropical convergence. When oceanic tropical convergence is active in month of May, but it is inactive. It becomes inactive during month of June, and there is this ITC-Z. When ITC-Z is active, OTC-Z become inactive. So during month of July, 15 July, by 15 July, monsoon covers entire country. It is in fully developed state. So this is MGO phase space diagram. These are the 8 phases of MGO. Whenever we talk of interseasonal variability or Indian region, then we talk of MGO. So the reason is that due to geographical coherence, it evolves. MGO is in phase 2 and 3 in Indian Ocean, and it is in phase 4 and 5 in maritime continents, and phase 6 and 7 in Western Pacific Ocean. So it MGO phases propagate eastward from here to here. So from this plot you can see there are years when onset has occurred in May and shown by star, and triangle shows onset date when onset of monsoon has occurred in month of June. So these are the results. During the period 1979 to 2030, 20 strong actual events, while 15 weak actual events were identified. Total 13 pre-onset years occurred during the period, while total 19 post-onset years were identified. Onset of summer monsoon is most favored by phase 2, followed by phase 1 and 4. Monsoon takes, I have already said that the focus of this study is on the progress of monsoon. So monsoon takes 41 days on an average to cover entire country. And I have done statistical analysis. From that statistical analysis what I get, fastest progress of monsoon was seen in the recent year 2013. In 2013, there was first one was the onset date over Kerala and Western Rajasthan. It takes only 15 days to cover entire country. And the year 2000 there was slowest progress of monsoon in the year 2002. These are the differences.
Thank you. Any questions? Questions, please. So people are very clear or people are clear. Okay. Okay, so next is Mahesh.
Good afternoon, ma'am. I'm going to talk on atmospheric column erosion concentration estimation using satellite data from 2007 to 2013. As we all know, this ozone is found to be in two different layers. That is from surface to 15 to 18 kilometers is we call tropospheric ozone, and from 18 and above 18 to 50 kilometers is stratospheric ozone. This stratospheric column is generally referred as a good ozone, and it protects life from sun's harmful ultraviolet radiation. Tropospheric ozone is generated by human activities, largely due to incomplete combustion of fossil fuels, transportation, and industrial emissions. And these are mainly affected by this ozone, NOx, and carbon monoxide volatile organic compound. These are called ozone precursors. This is a methodology to derive tropospheric columnar ozone and stratospheric columnar ozone. Mainly to input data from NASA satellites or ozone monitoring instrument with 25 kilometer resolution, and microwave limb sounder. The spatial resolution is around 200 to 400 kilometers.
So this doesn't have data points.
So recently INSET 3D launched, but it gives total columnar ozone from surface to
Total column.
total columnar ozone. But from this I am trying to derive tropospheric columnar, only tropospheric and stratospheric columnar. I'm separating these two components.
So you have used for this NASA.
NASA satellites. So in future I am going to derive from INSET 3D this tropospheric ozone.
So NASA gives you the column amount.
Entire columnar ozone from ozone monitoring instrument, sir, with 25 kilometer resolution. And one more satellite sensor is microwave limb sounder. It gives vertical profiles from stratosphere to some 50 kilometers. So,
Okay. So only the stratospheric goes.
vertical profiles, layer wise it gives. So before calculating tropospheric ozone, we need to fix the tropopause height, because I'm separating the stratospheric columnar ozone from total columnar ozone. So to calculate stratospheric columnar ozone, I have used Dessler algorithm 2005, and this OMLS gives it's a broad in spectral resolution, spatial resolution. So in order to collocate the points from OMI, I interpolated the stratospheric columnar ozone gaps, and the TCO, total columnar ozone from OMI, and calculated stratospheric columnar ozone. The difference between TCO and SCO gives a tropospheric columnar ozone with 100 kilometer resolution. So this validated, this derived TO validated with in situ observation, that ozone sound observations. But it is not, unfortunately, it is not about over India. So this ultimately this data is going to Bhuvan portal. NRS is having Bhuvan portal under NICES, National Information System for Climate and Environmental Studies.
What is that? What is that? Horizontal axis and vertical axis?
This is the temperature versus height. So this, before calculating stratospheric ozone, fix the tropopause height to calculate the stratospheric ozone.
So where is the tropopause in that?
15 kilometer, 15 to 18 kilometers.
Okay.
Tropopause is the altitude of the lowest temperature. That is called tropopause.
What is the vertical axis?
This is heights.
Height.
These are the results. This TCO is a direct. This is a direct from ozone monitoring instrument, OMI, and this is a derived tropospheric ozone with 100 kilometer resolution. These are few data gaps, and this data will be available soon in Bhuvan web portal under NICES. And NICES is a new initiative of ISRO. These are current ozone sound network. Unfortunately, we do not have published data over India.
So I used for validation Vietnam and Kuala Lumpur stations. These are the validation statistics. So with Vietnam, it is around R-square is 0.56 and Kuala Lumpur is 0.6. So I also calculated scatter index. Scatter index is it is a with respect to our data because it gives it is statistical analysis is must for validation of our derived products or derived results. These are few analyses.
So in situ, you do balloon sounding to get that in situ value.
Yes, ozone sounding. This we are planning for current next years. We are also planning for ozone sound facility. This from 2007 to 2012. Some trend analysis are done. It is showing slope with 0.003. When we multiply with 365 days, it gives troposphere ozone yearly growth rate is 1.1 Dobson unit per year. And the stratospheric ozone is 0.3 Dobson unit per year. These are some signal noise are there. We need to we need to do some signal processing. And this ozone variation anomaly, it's not anomaly exactly. Ozone deviation from 2007 to 2012 interannual deviations, and from 2010 to 2012 there is some positive significance is there. We are still incorporating some. We need to see some other results to incorporate this phenomenon. And stratospheric and troposphere ozone is around 85 to 90% in total columnar ozone, and troposphere ozone is 10 to 15. These are some emission of sources from natural emission sources and anthropogenic emissions. A few are both from natural and anthropogenic emissions. This during filing we also done some experimental case study. So this is lower troposphere and this is upper troposphere. During severe cyclone of filing, we have seen updraft in the ozone levels in the upper troposphere. That means this ozone levels are moving from lower troposphere to upper troposphere. But this is in normal condition. This lower troposphere values will be high. But due to severe cyclone, due to this deep convection over the Bay of Bengal, there is a updraft in the ozone levels in the upper troposphere. And during the severe cyclone of Philin and Marsin, there is a change in stratosphere percentage change in stratospheric columnar ozone. This severe cyclone of Marsin is 14/5/2013. That is wind speed of 15 knots, and stratospheric percentage is 74 in total columnar ozone. But same in Philin case, there is a 73% of stratospheric columnar ozone. This leads to this exchange between upper troposphere, lower stratosphere to upper troposphere. This is a poster. Thank you.
So he has this poster outside?
No, sir. We could not print it.
Proceed. No? Okay. Next is Mike Shesha.
Good afternoon, all of you, respected Balasa and dear friends. To understand the dynamics of climate, it is essential to have a long-term instrumental data. Unfortunately, we have a very limited yes of record or no record. Despite of it, we are able to reconstruct past climate based on different proxies, and cleaning is one of the best proxies. We have been discussing about how climate is changing and how different scenario of climate is going to be. But now I'm going to discuss about how exactly the tree growth relationship has been changing in eastern Himalaya. My title of talk is Climate and Growth Responses of Conifers along elevation gradient from Zemu Valley, North Sikkim, eastern Himalaya. I'm going to deal about the dendrochronology. Dendrochronology is the science of tree rings, rings which produce annually in nature. All rings are not annually in nature, but especially conifers and few angiosperms produce annual rings. And the annual rings behaves like a black box which record all climatic events. If we are able to harvest it, we can reconstruct it, all the climatic events. Here I am showing the tree of citrus deodara, which is a millennium year old, and already paper has been published in climate dynamics that is reconstruction of temperature more than 700 years. So the objective of my study is to develop well-developed reading chronology from the Zemu Glacier, close to Zemu Glacier or adjoining area, and to identify the limiting factor or climatic factor which is limiting the growth of conifers at that very places. Based on the climate or tree growth relationship, we are able to reconstruct past climatic events like temperature, precipitation, drought, stream flow, etc. Recently, a paper appears in Nature by Young et al. Who have reconstructed the insular variability based on dendrochronology and isotopic fractionation of tree rings. This is my study area. I have been conducted field trip from 7 different sites that are represented in terms of Lachen, Jema, Duzan, Khala, Talim, Yamthang, and Yabu. And Yabu is a tree line of Zemu Glacier. In second diagram, I have shown the tree line of Zemu Glacier and the Zemu glaciers. And for the analysis of tree, I have chosen the 4 species of conifer, that is Avis densa, Juniper recurva, Laris griffithiana, and Juniper stigmata. So this is the sampling technique of tree. We collect the tree core through the increment borer, which is shown in the diagram, and we take 2 core samples from each tree to present a homogeneous cross-dating sites, and then we polish it through the different paper of sandpaper, and by the help of studies of microscope, we measure the variability of ring width through the microscope. Generally, I have taken the elevational gradient of samples from the, if we talk about the higher edge of tree, the site that is 3,800 meters, that is the tree line of Zemu Glacier, to the lower site of that.
You remove a tree when you collect it?
No, sir. We just take 2 core samples by the introducing a borer to the tree. It will not harm the tree. Yeah. Generally, we take two core per tree. It will not harm the tree. We haven't reported any dead tree through this method. This is the well-established method since 1940 or back 20s.
So that tree core, that's the horizontal thing that goes in.
Vertically, I have introduced the borer and then take two core samples through the increment borer. Okay. So the methodology. Once we are able to measure the raw ring width of the tree, we apply different statistical method to harvest the signals. That is, I have approached the double dip trading method for the standardization of tree rings, and the first one is negative exponential, and the second one is 30-year spline method, by which we can standardize the tree rings. And then followed to establish the tree growth relationship. The 2 sample methods are available. That one in correlation, and another one is bootstrap regression, which is more sophisticated and gives a spatial variation or better result. So I have chosen bootstrap regression for the tree growth climate relationship. These are the tree ring chronology developed from the Zemu Valley that ranges from 250 years to 450 years from the different species like Avis densa from Yabu, Avis densa from Yamthang site. Yamthang site is close to Yabu site at the same altitude, almost same altitude. And then the Juniper recurva from the tree line side, and the Juniper stigmata, which is served from the Yabu tree line side. And another different chronology of Avis densa and from the lower sites like Jackson sites and Talim sites, Dozamkala sites and Jema sites I have developed. These 2 are more tree rings chronology from Lachen sites and one from different species, Laris griffithiana from Lachen. These are the time series flower which are developed through the 2 different statistical methods. After applying two different statistical methods, one is negative exponential retraining, and then second 30 years line. And the background line indicates the sample size. So moving on, tree growth relationship. The tree growth relationship to find out which climatic factor exactly limiting the growth of tree. So these plots are the regression coefficient divided by standard deviation coefficient plot, and these are the responses in terms of temperature, precipitation. Temperature in terms of mean temperature, maximum temperature, and minimum temperature. So what we have found is the maximum temperature. These are the maximum temperature for March, April for the tree line side, and this is another side which is Yamton side from the same species, also limiting the March, April temperature of maximum. So the March, April temperature, maximum March, April temperature limiting the growth of Avis densa at tree line. Along to the lower sides, we observed that the different species like stomata, which the precipitation of May-June. The precipitation of May-June is a limiting factor for the growth. Likewise, as we go lower down, the precipitation is playing the more critical role for the controlling of tree growth. So here, so the conclusion of this work is the temperature, especially maximum temperature, playing limiting factor for the growth of trees at tree line. So the maximum temperature may be reconstructed, or I have already reconstructed in my thesis, it's going to be complicated, for the 400 years. And since the precipitation limitation is there is a very variability, so we can't reconstruct it. And I would like to acknowledge my director, Professor Sunil Rajpal, Mr. Pradeep Kumar, and IMD, of course my senior Dr. Santosh Samasta, who helped me a lot during this work, and my friend Satyaman. Thank you. This is the tree line vegetations.
Which is the oldest, like, so far in India, how old can it go?
So far we have the Yadavital represented as citrus. They are the oldest tree. Citrus and juniper, the oldest tree in India, and which goes to, I think, 2000 years back.
It is very important to find out the visual strength, right?
What exactly the question is? Yeah, ring width.
So 4,000 years old
Tree.
is
Absolutely.
4,000
right?
This is, yeah, this is the tree which is more than 1,000 years old. Okay, from the western Himalaya, this is the tree. So what happens if we code this tree records the 1,000 years of climatic records. So now we are able to reconstruct exactly 0 year dating without any error. We can able to reconstruct 1,000 years of climate. So this is the benefit, and tree ring science is one of the best tools in paleoclimate reconstruction all over the world.
Okay, this area is dominated by southwest monsoon rainfall or western monsoon?
Southwest monsoon.
Well, I don't think you can distinguish that.
It's very difficult to distinguish.
The rains are not, that's what I think the rain can tell you.
So how do you know that this is 1,000 years old tree?
Good question. There is a method called cross dating. We take a sample from that very tree and another samples from the adjoining tree, and then we cross date. As we discussed in personalized classes, that there is a dating method. We assign exact calendar years of date to the rings. In this way, we can we count the rings and then assign the dates.
See, as the tree grows older, initially the width depends upon climate and all, but as the tree grows older, it starts forming thinner and thinner rings. So, how reliable is the liquid?
Okay. Basically, this is the endogenous factor which is responsible for the thinner or initial growth of higher growth of trees. For that, that very limitation, we used the training method. That's why I have used the double training method. One is negative exponential and another is 30 years spline, so that I can achieve that very noisy things from my data, so that I can harvest both two things.
So you apply method to remove those effects.
Yes, sir.
Okay, so thank you. So next is Mithun.
Good afternoon. Today I am here to talk about the small work I did over Bay of Bengal. I have collected the water vapor from over Bay of Bengal by participating in a CTZ cruise, and I have analyzed the stable isotopic composition of those water vapor samples, and the results I am presenting here.
Water vapor.
Yeah, atmospheric water vapor. As Prasenjit Ghosh taught us, these are the three major isotopically substituted water molecules, that are H2-16O, H2-18O, and HDO. There are certain other combinations are also possible, but their abundance is very small. So for our study, we restrict to these three, and here most of the people are not aware of the isotopic notation and all. So I will give the brief. I will give some introduction to that. Isotopic ratio R is defined as the abundance of heavy isotope, number of heavy isotopic molecules divided by the number of lighter isotopic molecules. Like R can be written as concentration of H2-18O divided by concentration of H2-16O, or concentration of HDO to H2-16O. This is how we represent the ratio. The measurement of this ratio is very difficult thing. Like in this mass spectrometer, we use for this measurement. So due to these difficulties in the measurement, there will be some mismatches between the measurement made in one lab and another lab. So we use a delta notation to avoid all these problems. Delta notation is nothing but the ratio between ratio measured in our sample with respect to ratio measured in a global universally approved standard minus 1 into 1000. This is delta value. So whenever I talk about delta 18O, it is nothing but the concentration of 18O divided by 16O minus 1 in my sample to that of the standard minus 1 into 1000. So similarly for delta D also. Delta D means deuterium. And another one term I will use here is fractionation factor, alpha. Fractionation factor is nothing but the ratio how the isotopic composition will change when it transfers from one phase to another. Like when evaporate, suppose here when rain is formed, cloud is formed from vapor, then water molecule is changing from vapor state to liquid state. So we take the fractionation factor as the ratio between the ratio in final liquid to the ratio in vapor. That's how this alpha is defined. And there are two kinds of fractionation observed in hydrological cycle. One is equilibrium fractionation and another is kinetic fractionation. Equilibrium fractionation is nothing but when two phases are in equilibrium. Suppose you have a closed bottle and some water over it. So if you keep it for over time, so the area inside the bottle will become saturated with respect to that water. So the number of molecules going into the liquid phase and number of molecules coming out of liquid phase will be equal. In that situation, this fractionation is just a function of temperature, as defined as alpha is equal to exponential of 1 by t. 1 by t relation is there. And when I talk about kinetic fractionation, it is just caused by the change in the diffusion. When these molecules diffuse, this lighter will diffuse faster, heavier will diffuse slower. So that is called the kinetic fractionation. The first one is just temperature control, and second one is depend upon what kind of flow, what kind of diffusion. So coming to some data, this is a paper published in 90s. This figure shows some data which is presented in 91. I have presented around 400 isotopic measurement of water collected from precipitation, lakes, everywhere, and there is you can see there is a very good linear relationship between hydrogen isotopic composition and oxygen isotopic composition. So that relation is delta D is equal to 8 times of delta 18 plus 10. So this relation comes from the ratio of the fractionation factor that you can see, that changes from around 9.5 to 8.2 when temperature changes from 0 to 30. So somewhere around 8 is observed in meteoric water, means global waters, and this alpha, first one I have shown, this alpha, that is for equilibrium fractionation only. When it undergoes kinetic fractionation, when it's a diffusion dominated fractionation, then this fractionation for deuterium is lesser. You can see in the first law, when fractionation occur in equilibrium condition, fractionation is more for deuterium, but in the case of diffusion fractionation, that is kinetic fractionation, fractionation is lesser for HDO. That just because of the mass difference. So we defined a parameter called dxs. Dxs is nothing but delta D minus 8 delta 18. Now this definition is coming from this global relation. And another thing, since I have collected the water vapor over Bay of Bengal, so I will briefly talk about how we can calculate the isotopic composition of the water vapor. Water vapor which is evaporated from ocean or any open water body. You know, this evaporation flux is directly proportional to the deficit in water vapor, that is saturated mixing ratio minus actual mixing ratio. So we apply this equation for water molecule, that is basically H2C now, and the same thing we will apply for HDO and H280 now, and we will take the ratio and we will calculate the delta value. So this is a schematic representation for this evaporation model. Suppose we have an ocean. This global ocean average delta value is considered as 0 because that is the reference we are taking. So in ocean we have an isotopic ratio R ocean. Then we will have a saturated micro layer over the ocean while evaporation. So since this micro layer is saturated with respect to ocean, we can apply equilibrium fractionation factor over there. Then we can calculate the isotopic ratio in that layer. That is just alpha equilibrium into R ocean. But the atmosphere above that will have a structure of humidity like this. Here humidity, I didn't take the relative humidity, instead of that I took the relative humidity with respect to the SST, instead of taking the actual humidity. So it will have an exponential decreasing nature. So due to that sharp gradient just above this micro layer, it will be highly like this all processes are dominated by diffusion. So there will be a kinetic fractionation over that region. So the final ratio in the evaporated water will be like this equation. This equation you can simply see the top one is just the difference in isotopically substituted molecule, and the bottom one is just the difference in humidity.
What is RV?
Sorry?
What is this? You have RA, that is the
Yeah, that is a atmosphere.
and RV.
RE is the RE is evaporation flux.
Evaporate.
Yeah, and RA is the whatever the vapor isotopic composition previously existing in atmosphere. But the problem with that equation, we don't know the ratio in atmosphere. So people use closer assumption where RE is that whatever the isotopic composition of vapor is equivalent to the isotopic composition of the evaporated water. So you can simplify the equation. So we get the equation for RE like this. Using this equation, you can see that when there is a negative relation of humidity, dxs with respect to humidity, and a positive relation with the SST. But this positive relation is not that like that slope is very small compared to whatever it is observed in dxs with respect to humidity. So this will give us an opportunity to look at the past humidity variation and all by looking at the dxs in ice cores. So my objective of this work is just to characterize the isotopic composition of the source vapor. And another thing is what are the meteorological controls on this delta 18 and delta D over ocean. So I have participated in the series that cruise during 2012 monsoon over Bay of Bengal. These are these points corresponds to the places where I sampled the vapor. This is the equipment I use for sampling the atmospheric vapor. Basically what I did is you can see a pump here, and this pump will suck the air from the outside atmosphere, and it is passed through a glass column here, and this glass trap is immersed in a alcohol which is cooled up to -80, below -80 using liquid nitrogen. So whatever the moisture inside the air will condense inside the trap, and I will take out the moisture and I will do the mass spectrometry analysis in mass spectrometer. This is the mass spectrometer we have in our institute. Coming to the time series of water vapor. The first two panels shows the time series of delta 18 and delta D, and this is the dxs, and other meteorological parameters are also plotted here, and this shaded region corresponds to the rain spell during the cruise. You can see there is a 3 deeps also observed in the isotopic composition during the rainfall, and
So the operation is down. That's what it means.
no, that is just, that I will come to next slide. So you can see the pressure drop during all these events, and okay, I will go to next slide. Here is the relation that I was talking about, the dxs with respect to humidity, and this is the previously published data. This is measured in Southern Ocean, and this is where our data lies. So this is the delta D, delta 18 plot. Since we are in tropics, we will our temperature is higher, so fractionation is lesser. So we will have somewhere here. Our data lies here. Where you go to polar region, the vapor will be somewhere here. So what I will conclude from here is we also observed a relation between dxs and humidity, but R square value is very small compared to whatever reported previously. But you can see the slope is more or less same. So it may leads to an existence of this global relation between dxs and humidity. This is the back trajectory analysis I have done to understand the probable source of moisture. This is the relative humidity, and this is the height of the parcel during its. So you can see during southwest monsoon, because of lot of rains in this western Ghats region, the relative humidity is very less here. And whenever it reaches to my sample collection location, these are these black dots, so it acquires the moisture from Bay of Bengal. And here what I plotted is the delta 18 of the vapor. This is the delta 18 of vapor, and this blue one is the rain rate average along the trajectory for past 1 day. So you can see it is also following the same trend, and this line shows the isotopic composition estimated using the equation that I have shown previously. So you can see whenever there is a non-rainy day, this is almost close to the estimated isotopic composition, but during rainfall there are large dips. So this difference I have plotted with respect to the averaged rain rate along the back trajectory. There is a relation. So recently one more paper published telling that this depletion in the isotopic composition of vapor is due to the past rainfall activity. So this means that when rainfall occurs, this rainfall will evaporate to the atmosphere, or it will equilibrate with the atmospheric moisture. So that's why we are getting more depleted vapor than what we expect using that model. So conclusion, these are the results. First time I have measured the delta 18 and delta AD of atmospheric vapor of Bay of Bengal, and DH relation seems to be valid in Bay of Bengal but less prominent, and the model estimates are good enough for non-rainy days, but during rainy days it is affected due to the re-evaporation from raindrops.
Any question? No? Okay, so he is Naveen Chandra. So who is Hitesh? Take here. Will you last person?
Good evening to all of you. So my topic is the measurement techniques of CO2. As in past 10 days, you have already know about the importance of atmospheric CO2. And we are continuously dumping around 46% CO2 in every year. So this is my just the sake of completeness. I'm showing this slide since it is already discussed in the last previous day. And from this slide, I want to say that the annual growth rate of CO2 is continuously changing with respect to time. So if you will see the atmospheric value of CO2, it's around 450. It's crossed around 400 ppm in recent December of 2030. But the changes is very less in comparison to the atmospheric CO2. So if you want to quantify these changes, this 1.9 ppm, 1.5 ppm, 1.6 ppm, 1.3 ppm per year. So we want to monitor the atmospheric CO2 in the accuracy of this minimum changes. So if our data is not much accurate, so we are not able to say that between these years the atmospheric value of CO2 is changing. So for investigating the global climate change needs extremely precise and accurate measurement of CO2. Since net change in the atmospheric CO2 level is very small compared to its ambient concentration, and the World Meteorological Organization WMO already recommend that the 0.1 ppm of uncertainty should be in our data. So there are several methods for measuring atmospheric CO2. One is the gas chromatographic technique. Another one is the IR spectroscopy. IR spectroscopy covers the non-dispersive infrared radiation technique and cavity ring down spectroscopy technique. So I will briefly introduce all these techniques. This is the basic principle of gas chromatography. From this slide, I only want to say that we physically separate the atmospheric value of CO2 from the sample, and this is the heart of our gas chromatography. This is known as the column. This column will separate the ambient CO2 from the sample, and with the help of this FID detector, the field ionization detector will calculate the atmospheric concentration of CO2. But the disadvantage of this technique is that the precision in data is very very bad, and that is around plus minus 1%. So for the global climate change monitoring the CO2 value, we cannot use this gas chromatography technique. Another one is the non-dispersive infrared radiation technique. It contains the dual cell analyzer, that is, one is the sample cell, one is the reference cell, and this is a monochromatic source. It will illuminate the radiation from both cells, and on the basis of difference of the intensity of both cells, this detector will on the basis of the difference of absorption of both cells, we can calculate the ambient value of atmospheric CO2. But the disadvantage of this technique is that any noise introduced by this sample cell, by this higher source sample cell, reference cell, these detector noise will subvert the sensitivity of our system. So, for making the accurate measurement with the help of this technique, we need to control a lot of uncertainty parameters. And for this, some of the uncertainty parameters is water vapor, gas temperature, gas pressure, baseline rate, and laser stability. I will only emphasize on the water vapor. Water vapor can introduce error in our atmospheric data by direction error and spectral interface. Since the CO2 absorption band and water vapor band are almost near to each other, so with the help of that, since the India technique is measuring the absorption strength due to the absorption of the sample, and so by introducing water vapor, due to spectral interface, it can destroy the sample. It can cause the error in sample. And another one is the dilution error. The dilution error can underestimate the value of CO2 by basic principle. We know that P is equal to nRT, and at constant pressure and temperature the number density will be same. But if we introduce 1% or 2% water vapor, so for conserving the water vapor, that number density, some CO2 molecule will be goes out, so it will introduce some error in the CO2 value. And this one is the lab experiment. This one is the temperature dependent of the absorption of CO2. So you can see that by this graph, 3 ppm can cause the 3 ppm per degree centigrade can cause the drift in CO2 value. So WMO has 0.1 recommended 0.1 ppm uncertainty, and it is 3 ppm. And due to this 3 ppm, so we need to control all these variables for getting that 0.1 ppm uncertainty. So this is a previous slide. I told you that the dilution error can cause underestimate the CO2 value. So from this graph, this is the lab experiment. From this graph, you can see that in the water vapor vary from 8,000 ppm to 40,000 ppm. Then the error can cause from 6 ppm to 12 ppm. So for getting that much 0.1 ppm accuracy, we need to reduce the water vapor from 14,000 ppm to 100 ppm. So for that, keeping in mind in all these types of uncertainty, we have set up this setup in our lab for measuring the accurate value of CO2. This is our analyzer system, and these are for controlling CO2. And this is a natural dryer. It will reduce the dew point of ambient sample from atmospheric value to minus 40 degrees centigrade. So approx the water level will come to 100 to 200 ppm. So making the measurement very accurate. We are calibrating our instrument by 4 cylinders continuously. We have imported this cylinder from Nova, and these are very expensive. The cost of this cylinder is very expensive. So for making continuous measurement by this setup, it's very cost wise it is very high. So this is our lab calibration of that NDR system. So it needs every 2 hour calibration. So for making accurate measurement, we need to calibrate our instrument within every 4 hours by those cylinders: 350 ppm, 380 ppm, 400 ppm, and 440 ppm. This is the stability check of instrument. So this technique is very cost effective and human influence. So we need to continuously check all these parameters and all these values. So it's very tricky, very tough and very tricky. Now another technique is the cavity in-down spectroscopy. In the NDR technique, we were measuring the absorption strength of intensity. But instead, and the error was causing due to the source interface, sample line interface, detector interface. But instead of measuring the strength of absorption line, if we measure the decay time of intensity, we can calculate very precisely atmospheric value of CO2. So this is
decay time of what?
Decay time of intensity. There are 3 mirrors. This is the laser source. It will inject the light, and by the reflecting the intensity between 3 mirrors, it will decay with respect to time. Since there are the absorption molecules, they will absorb the intensity, and intensity will slowly decay. And these 3 mirrors will helpful to increase the path length around 20 kilometers.
Softening by CO2?
Yeah. So this is very good technique, and in previous NDR technique we need every 2 hour calibration if we want to get a very accurate measurement. But with this technique, this technique is very stable and very precise. So this is the sensitivity study of this technique, and we put the value of CO2 for 24 hours. CO2, and it can measure 4 gases simultaneously. This technique: CO2, CO, CS4, and water vapor. So with the help of that water vapor, we can correct our CO2 for direction correction, and due to the mechanism of that technique, we get very precise measurement of CO2 without any human effort. And this technique needs every 15-day calibration instead of 2 hour calibration in NDR technique. So the precision of CO2 within 15 ppb, CO2 will have 5 ppb, and CS4 is 0.6 ppb. So this one, the advantage, and this is some results for November month over Ahmedabad. And this is CO2, CS4, CO, CS4, S2. I will not go into the details of these variations. And now the question is this the end of NDR technique? I will say certainly no, because if we want to measure CO2 within the accuracy in point decimal, then certainly this technique is very good for continuous measurement. But if you want to measure some emission, like if you want to measure the industrial emission, then that is very costly technique. The price is very high for that type of instrument. So for only the emission measurement, we cannot afford for that types of money. So for emission study, we can use the NDR. It is very cheap and reliable for every worldwide. So thank you.
Okay, the last part. How many slides you have?
20.
I had given instruction very clearly, we should not have more than 10.
Yes, sir. But I will finish it out.
Huh?
I will finish within 5 minutes.
Okay, I hope you know. Please remember, this is not a full talk. So, tomorrow, don't have more than 8 slides. I think I saw many people having more than 10 today, in spite of telling you very clearly yesterday. So, because you don't have that much time. And we need to cover 20 people in a day, after that. Okay?
Good evening. I would like to present some of the results of our study. Decadal sea level variability in the tropical Indo-Pacific Ocean. I would like to be brief because I have already presented these results in poster outside. So I would like to tell some background on which I am standing by studying decadal variability in the tropical Indo-Pacific Ocean. That is, I will tell you some of the purpose, like Meal et al. In 2009, he discussed the importance of studying the decadal variability or low frequency variability while attributing the long-term changes that have been.
Let's move to the work.
Yeah.
I think, another important point tomorrow again. I think we want to really assess, in fact, discuss your work. So don't elaborate too much on the literature.
Yeah. And we have two observations of decadal variability in the Indo-Pacific Ocean. One is used by satellite altimetry by Lee and McFadden in 2008, and one is by using long-term tide gauge records by Fengeta. And what is the main problem we are facing while studying the decadal scale variability is the incomplete description due to limited observations. Like we have a large spatial coverage from satellite altimetry, but poor temporal coverage. And we have long-term tide gauge records, but its spatial coverage is very low. So what we adopted to use a numerical model and validate it with available observations to infer the decadal variations. So we used a general circulation model, NEMO, forced by ERA 40 wind. And we computed the steric sea level anomalies over the upper 1,000 meter layer of the tropical Indo-Pacific Ocean by using the equation of state of water. And we use a seasonal trend decomposition procedure for the filtering the data to get a decadal signal. And we use a simple statistical analysis on the filtered data. This is the standard deviation of the steric sea level over decadal and interannual time scale, which shows the maxima of sea level variability at these two time scales. And like Northwest Pacific, Southwest Pacific, West Australian coast, Eastern Equatorial Indian Ocean, Bay of Bengal, Southwest Indian Ocean. And we validated the steric sea level evolution over these regions with satellite altimetry and tide gauge observations. That has been shown in the left panel is comparison with altimetry, and the right panel is tide gauge. That gives pretty good comparison. And first mode of EF analysis over these two time scales shows that at interannual time scale there is a tendency for the co-occurrence of primary modes like ENSO in the tropical Pacific and IOD events in the Indian Ocean, but at a decadal time scale, the primary mode that is explaining 47% of the total variance stands mainly for the variability in the Pacific Ocean that is purely independent from the Indian Ocean. And here we are assessing the regional variability by simple correlation and regression analysis with the model wind dataset over different regions. And we can see that the most of the decadal variability is explained by the upstream wind stress curl away from the equator and wind stress in the equatorial regions. And some of the regions like the West Australian coast and the Bay of Bengal is controlled by the remote forcing from the equatorial region. And this decadal variability assessed from the NEMO model
is highly sensitive to the wind forcing, that is ERA 40. So we have assessed the decadal evolution of wind from 3 other reanalysis wind, NSEP, 20th century, and WS wind field. And that gives pretty similar evolution at a decadal time scale of wind stress. So we are pretty confident about the decadal forcing on a model. And so this is a summary. This amplitude of sea level decadal variability is nearly half of the interannual variations. And the zonal wind stress is found to be the major forcing for the decadal variations in the tropical region. And the decadal variability in the 2 basins are found to be independent. And the West Australian coast and the Bay of Bengal region is forced remotely. And the Southwest Indian Ocean also stand independent. And if somebody want to know the more details, this has been published in Climate Dynamics. Thank you.
Okay. Well, I think now if you look at today, at least I feel I am benefited in the sense, even though I'm sure you are all talking to each other,